Right, so just like Julian, we were being asked to think about what we would like to talk about here today. And so I guess we all work on a lot of different things. And so, but I thought that it would make, given that I'm here for a Career Achievement Award, it would make most sense to talk about something that has been with me throughout my entire career, ever since I was a student, and that I'm still working on today. And for me, that is the early Earth. Also, some call it deep time. And of course, the way I look at the early Earth, that also implicates the mantle. Mantle geochemistry is something that has also been my interest ever since I was a student and that I still work on. And if I talk about the early Earth and the mantle, I have a chance to talk about my favorite element, hafnium, and my favorite rock, komatiites. And so this is what I'm going to do today. As you all know, the heterogeneous nature of the terrestrial mantle in terms of its chemical composition and its physical properties is well known since a long time. But the origin of these heterogeneities and their residence time and their mixing time scale in Earth's mantle is not so well constrained. And this is what I'm going to address today from the perspective of the early Earth, especially that offered to us by komatiites. So some of these heterogeneities have been inherited from the time of planetary accretion and crystallization of the primordial terrestrial magma ocean that I think we begin to believe really was there. And komatiites, of course, are one of the rock types that is giving us a lot of clues about the fact that we probably did have a terrestrial magma ocean, as you will see. Some other heterogeneities that we see today are probably due to the production of continental crust, extraction of continental crust from the mantle throughout over geological time, and the recycling of some of these crustal materials back into the mantle through subduction zones, like Terry mentioned earlier, and in some cases followed by prolonged storage at depth for billions of years. Others are due to changes in Earth's thermal regime, affecting the melting process through time. And yet others are simply due to sampling bias, as much as I hate to say it, as only a tiny fraction of the mantle is accessible for study. And even that fraction likely is not directly representative of the mantle as a whole, but there's precious little we can do about it. We can only do the best we can with what we have, and this is what we're trying to do. So today, limiting myself only to what komatiites can tell us, and also being limited in time, I will focus on the first and the third point, and I may not even get as far as to the third point, in which case you will just have to take my word for that. So, in order to address the first point, we used, or rather measured, combined hafnium-neodymium isotope systematics in komatiite basalt systems worldwide, ranging in age from 3.55 to 0.9 billion years. In order to establish the composition and the evolution of deep mantle sources over time. And the green stars on this map are the komatiite basalt systems we have looked at so far, and we're working on several others at the moment and just got funded to work at many more others. And so I hope that this work will be something I can continue for the next 10, 20 years, whatever is left. So because komatiites formed by large degrees of melting in deep mantle plumes, the compositions approach that of mantle peridotite. So we can pretty safely, for the remainder of this talk, assume that komatiites have recorded the chemical and isotopic characteristics of their mantle sources. This is the underlying assumption. So komatiites deliver messages from the distant geological past. And although essentially no komatiite that we know of so far is pristine, there is still lots of important information in these messages if only we can learn how to read them. And by that I mean that we need to find ways of getting around crustal contamination that has affected some komatiites and secondary alteration that has affected almost all komatiites. If we cannot get around this, then the data we collect will scatter widely at variance with normal magmatic processes, and in this way mask the signal, the primary source signal carried by these komatiites. So in order to do this, we select samples so as to include only those least altered, by far the freshest komatiites we can find. And whenever they have been preserved, we separate relic magmatic clinopyroxene, and those are the materials that we're working on. And so in this way, with the best preserved sample selection strategy, and of course very careful analytical work, komatiites are some of the hardest rocks to measure precisely and accurately. We manage, despite the non-pristine characters of most komatiites, even if we follow those 2.1 and 2, to tease out important information about these very old ancient rocks about the early Earth. And so in this way, we managed to see through the complications arising from crustal contamination and secondary alteration and get to what we really care about, which is the mantle. And so in this plot here, I show you initial epsilon neodymium compositions and initial epsilon hafnium compositions as a function of age, only for best preserved samples in Klein-Pyroxene. And so when data are selected in this way, you can see that we obtain very nicely coherent and ordered trends for both isotopic systems, and that the data increase gradually through time overall, starting with values from close to 0 for the oldest komatiites up to values of +10 and +18 respectively for neodymium and hafnium isotopes for the youngest komatiites. And I should probably point out, I would like to point out that it looks like there is not a whole lot plotted on these two plots here, but I will say that each of these symbols, different colors symboled, represent a specific individual komatiite basalt system, and you can see that there are error bars associated with each symbol, and this is because each symbol is the mean of tens and tens and tens and tens of measurements that we have made for each locality. So there are literally hundreds and hundreds and hundreds of data summarized on this slide. And so there are these few dots there represent many years of my life. And so here I show you again, to your right, the initial hafnium and the neodymium isotopic compositions, plotted as a function of each other this time. And to the right, a truly time-independent plot, the time-integrated source parent-daughter ratios for the two isotopic systems, this time plotted relative to the terrestrial evolution curve. And despite the fact that, as you can see, by far most of the data plot on the terrestrial evolution curve, which indicates normal depleted mantle evolution from the late Archean through the Proterozoic and up until today, there are some notable exceptions. And the most striking of these are the early Archean komatiites, which I have highlighted with arrows here. And what is exceptional about those is that, as you can see, they all plot systematically above the terrestrial evolution curve in both types of plots, due to elevated time-integrated lutetium-hafnium ratios for a given time-integrated samarium-neodymium ratios, which are over here, on the other side to your right, translates into elevated epsilon-hafnium compositions for a given epsilon-neodymium composition. And this feature probably is due to the derivation of these early Archean komatiites from remelted crystallization products of a primordial magma ocean in deep mantle plumes, which in turn imply the gradual eroding away of distinct early primordial silicate reservoirs somewhere in the mantle that these very early lavas were sampling or were tapping at that time. And so we were able to reproduce the chemical and isotopic characteristics of these early Archean komatiites by melting a depleted source created or formed by the crystallization of calcium and magnesium perovskite in a magma ocean, 4.5 billion year old magma ocean. And what I'm showing you here are the trajectories, or rather the evolution of the time-integrated parent-daughter ratios for the hafnium-neodymium isotopic systems as a function of the proportions of the major crystallizing phases in the sources of these komatiites. And what you can see is that these komatiites formed by melting either cumulates or residual liquids formed in a magma ocean that had undergone different degrees of differentiation of different proportions of calcium and magnesium perovskite very early on. And so this notion that the early Archean komatiites are actually tapping primordial silicate reservoirs, being distinct, hiding out somewhere in the mantle, is further supported by the fact that, again, the time-integrated source parent-daughter ratios for these komatiites in the sources of these komatiites decrease systematically over time, indicating the back mixing into the deep mantle of a relict, in this case early enriched reservoir, also known variably as the missing or the hidden reservoir, whose existence was first inferred from the hafnium-neodymium isotope mass imbalance between Earth's major terrestrial reservoirs, the mantle and the crust, relative to chondritic meteorites. And so, like I said at the very outset of this brief talk, that one of the major outstanding questions at this point is at which time scale these primordial distinct silicate reservoirs hiding somewhere in the deep mantle, at what time scale are they being mixed back into the convecting mantle? And if you just look at this slide, it looks like we're looking roughly at a couple billion years. But in order to much more precisely assess this mixing timescale, it is better to look at the extinct radioactivities 142 neodymium and 182 tungsten. And this is because the excesses and the deficits of these two extinct radioactive systems, of these two extinct systems, they don't die. They just get diluted by material extracted from the mantle at a later time after the excesses and after the anomalies of these two isotopic systems formed very early on. And so here you can see a global compilation of 142 neodymium for all Earth's oldest rocks, as well as for modern mantle-derived rocks. And as you can see, it looked like, indeed, that the early Earth went through a transient heterogeneous regime very early on, prior to onset of normal mantle dynamics, and that these heterogeneities were inherited, as I said earlier, from the time of accretion and from the crystallization of the terrestrial magma ocean. And then these heterogeneities have been gradually mixed away or diluted by mantle convection on a timescale of a couple of billion years. This slide shows you exactly the same as the previous slide, except that I have highlighted the komatiite data in green so we can look at it a little bit more closely. And I'm sorry the age scale goes in the opposite direction from the previous slide, but I wasn't going to replot it just for one talk. So there are several important informations to draw from this slide. And the first one is what we saw already, that we have both positive and negative anomalies for 142 neodymium, up to 20 ppm and down to 20 ppm. And these could only have resulted from crystal liquid fractionation in the silicate earth, while 146 samarium, the parent 142 neodymium, was still alive, so within the first 500 million years of Earth's existence. And the next thing you can notice is that the magnitude of these anomalies, they systematically decrease over time, and this is exactly the same thing as we saw for the decrease in the time-integrated lutetium, hafnium, and samarium neodymium ratios over time, indicating that these heterogeneities are being mixed gradually back into the convecting mantle. And the last piece of information that you see on this slide is that the youngest rock, in terms of 142 neodymium isotopes that we know of that have both positive and negative anomalies, are 2.7 billion years old, which at this point so constrains the mixing timescale in the Archean mantle to 1.8 billion years. And we see pretty much the same systematics, at least at a first glance, for 182 tungsten. You can see in the Archean we have both excesses and deficits, and at 2.7 we have the youngest rock that shows excesses and deficits. And so this also, just like 142 neodymium, indicates a slow mixing timescale for the Archean mantle of the order of 1.8 billion years. And the only way that these excesses and deficits could have been there, again, would have been from silicate liquid crystallization in the silicate earth or from core formation. And in both cases, when 182 hafnium, which is the parent of 182 tungsten, was still alive. So this time, this is an even earlier timescale, within 60 million years of the age of our planet. But this is where things stops being the same and things gets a little bit more complicated, because as you saw on one of the previous slides, from modern mantle-derived rocks, we do not see any 142 neodymium anomalies, but we do for 182 tungsten, lots of them actually, in all of these different places, although just recently the Untunged Java point has been put into question, but that still leaves a lot of tungsten isotopic anomalies in modern mantle-derived rocks that tells it that there might still be some primordial reservoirs, very early primordial silicate reservoirs left in the mantle today. And it also tells it that it looks like that tungsten and neodymium isotopes have different resiliencies to mantle homogenization processes, and that tungsten is more resilient than neodymium. And this is probably linked to the different nature of these two elements, maybe to different length scales of their heterogeneities, maybe to different locations in the mantle. And I guess my time is up. And this is what I was expecting, but if it isn't, then I could go on and talk some more about what komatiites are telling us. 5 more minutes, so I can go on and talk a little bit more about what komatiites can tell us about probably one of the most controversial yet still unresolved questions in modern geology, which is the timing of onset of plate tectonics, which is very apropos given that this year we are celebrating the 50 years of plate tectonics, and we have one of the inventors in the room, Dan McKenzie. So this was a conclusion slide I just put in case I was cut off here, but let's go a little further. So what I want you to look at here is just that red stippled box there. And so this is, again, back to some of these early Archean komatiites that I just showed you, carry a very strong isotopic signature from the terrestrial magma ocean. But some of these komatiites in the Barberton greenstone belt have been overprinted by something else. And what you can see here, where there is an arrow, is that in terms of the epsilon hafnium isotopic compositions, they're extremely positive, much, much more positive than anything I've ever seen. And that goes for the clinopyroxene as well. And I have had to convince so many people about the truth of this signal that I have spent 4 years reproducing the data over and over and over again and separating more and more and more clinopyroxene until this is written in stone. This is what it is. But not only that, what is really weird, and the only time we've ever seen that, is that the neodymium isotopes, they are not even normal. They are essentially negative. Okay? And so in order to get extremely positive epsilon hafnium extremely positive or radiogenic hafnium isotopic compositions and negative epsilon neodymium, you need a mantle source with a high time-integrated lutetium hafnium ratio and a low time-integrated samarium neodymium ratio. And here to your left, a bit exaggerated, I show you a schematic of what the trace element pattern of such a mantle source should look like. And on the right, you have the actual trace element patterns of these particular komatiites. And what they're characterized by is slightly enriched light rare earth elements, giving rise to low samarium neodymium ratios, and a prominent hafnium anomaly that gives rise to high lutetium hafnium ratios, exactly what we're looking for. Now, there are 2 ways that we can obtain this. One is by the presence in the source of these komatiites of a phase that fractionates these 2 isotopic systems, which usually are correlated with each other, whereas here they're anti-correlated, and in opposite directions. And the only phase we know of is the lower mantle phase, magnesium wustite, because it is hafnium is compatible in this phase, but the rare earth elements are not, and you see the systematics here. However, this explanation is not really it doesn't work very well when you talk to high temperature, high pressure experimentalists, because they will tell me that then the proportions in the residue will have far too much magnesium-wustite compared with perovskite, and this simply doesn't work. This is at odds with all normal estimates of lower mantle compositions. So the other way that you can get radiogenic hafnium and unradiogenic neodymium is if these komatiite magmas had assimilated either in their source or on their way to the surface a small fraction of fine-grained sediment, because most of the hafnium budget, like 99% of hafnium, is in zircons. Zircon is a heavy refractory element, and so therefore tends to get deposited in fluvial and coastal settings. And so the very fine-grained sediment, which is left after all the zircons and therefore all the hafnium has been dumped out, they go out and become pelagic sediments in the deep oceans. And so they will have low to normal samarium neodymium ratios and very high lutetium hafnium ratios. And so over time, they will grow in exactly the isotopic signature that we are talking about. And so due to the very unusual composition of seawater in the early Archean, the normal sediment on the seafloor, or the ocean floor, back at the time of the Barberton komatiites in the very early Archean was chert. And as many of you probably know, there are lots of chert intercalated with komatiites in the Barberton greenstone belt. And cherts actually have very high, chemically speaking, they have very high lutetium hafnium ratios and moderately high samarium neodymium ratios, or I should say moderately low, which should give rise to the isotopic signature we're looking for. And just recently, this was finally measured, and as you can see, they have extremely radiogenic hafnium isotopic compositions and negative epsilon neodymium. So this really opens the possibility that the signature that we're seeing in these very old barberton komatiites are due to incorporation of sediment into these lavas. And so then the question is, was the sediment, the chert, incorporated into the source or as contamination onward to the surface? And the mass balance is very quickly done. It has to be a source signature because there is so much hafnium and neodymium. Well, let's say there are the same amounts of hafnium and neodymium in a komatiite lava as there is in the chert. So if you were to do that just by simple crustal contamination at the surface, then you would need so much chert in order to be able to modify the hafnium and neodymium isotopic composition to the chert values that you would end up crystallizing a granite and not a komatiite. And if you throw in fractional crystallization into the picture, then the komatiite, or the contaminated komatiite, which now looks more like a granite in terms of its silica content, we will not even have reached the target isotopic signatures before the lava has crystallized. So this is a source signature. And if you see trace of something that was once on the surface in a very deep-seated mantle source, there's only one way it could have come there, gotten there, and this would have been by subduction. So this indicates that subduction took place at 3.5 billion years, which is the age of these komatiites, but probably already at 3.7 billion years, which is the age of the church, and which is the age we need for the mass balance calculation to give us the result that we have obtained. And there is one more geochemical clue to this. This is the hafnium-samarium ratio that many of you know is one of those constant trace element ratios that never change in any terrestrial mantle-derived basalt. So it seems to be indifferent to any sort of normal magmatic process, except when zircon is involved, because zircon involves all of the hafnium. And you can see here in blue and red and green the komatiites that has the sedimentary signature have very low hafnium-samarium ratios, whereas other formations, also from the Barberton greenstone belt right next to the komatiites, that we have measured with the unusual signature, they have normal hafnium-samarium ratios and normal hafnium and neodymium isotopic compositions. So I think I will simply leave you with the conclusions. And it might have been more than 5 extra minutes. I'm sorry about that.